All right, what if I told you there's a way to take a really tough optimization problem, the kind where you're trying to find the best possible answer, and turn it into a super simple yes or no question, and then solve it ridiculously fast? Well, that's exactly the superpower we're going to unpack today. It's called binary search on the answer.
So the whole idea boils down to this. Can we really find that one single perfect answer to a problem, not by brute forcing every single possibility, but just by asking a few really smart yes or no questions? I know it sounds a little bit like a magic trick, but trust me, it's an incredibly powerful algorithmic pattern. Okay, so the real secret sauce here is all about how we reframe the problem. Instead of hunting for that one best value, we completely change the game. We start making simple decisions, just asking ourselves, hey, is this value good enough? And that shift right there, from optimizing to just deciding, that's the absolute key to the whole thing. So, what makes this even possible? Well, it all comes down to finding a tipping point in our answers. And to do that, we have to lean on this really foundational concept. It's called the monotone predicate. So, what on earth is a monotone predicate? Don't let the name scare you. It's really just a fancy way of describing a yes or no question where the answer flips from no to yes exactly once, and then it stays yes forever after that. Seriously, just think of it like a light switch. Once you flip it on, it stays on. Just picture this for a second. Imagine all your possible answers are laid out in a big long line. At the beginning, they're all no, no, no. These are not feasible solutions. But then you hit this magical boundary point and bam! Suddenly everything after that is yes, yes, yes. Our entire mission, our whole goal is to find that very first yes in the most efficient way we can. Okay, so we've got our line of no's and our line of yeses. The big question is, how do we find that boundary super efficiently? Well, that, my friends, is where the classic binary search method comes into play. And the process itself is honestly beautifully simple. First, you just define your search range. What's the absolute lowest and highest possible answer? Then you jump right into the middle of that range and you ask your big yes or no question. Is this middle point feasible? And depending on whether you get a yes or a no, you get to throw away half of your entire search range, just like that. You just keep repeating this, chopping your search space in half every single time until you've completely zeroed in on that boundary. And this is where you see the real magic, the true power of this technique. Instead of checking every single option one by one, which would be, linear, we only have to make a logarithmic number of checks. Now, for a massive search space, that's literally the difference between a program finishing in seconds versus taking hours or even days. The total time is just the number of checks. That's the log of the range, multiplied by however long it takes you to ask your yes or no question. All right, theory is great and all, but let's make this stuff concrete. Let's put it into practice. We're going to use a super famous problem to see this pattern in action. It's called Coco's bananas. So here's the deal. We have Coco, our monkey, and she's got a bunch of banana piles of different sizes. She also has a deadline, a limited number of hours, let's call it H, to eat them all. Our job is to find the absolute minimum eating speed, K, that she needs to finish every last banana on time. See that word minimum? That's our optimization problem right there. Okay, so how do we bring our new superpower into this? We've got to turn this optimization problem into a decision. So what do you think? What's the simple, straightforward yes or no question we can ask about Coco's eating speed? And boom, here it is. Our predicate is simply, can Coco finish all the bananas within each hours if she eats at this specific speed? And think about it. This is totally monotone, right? If she can finish all the bananas eating at a speed of, say, 10 per hour, she can definitely finish them if she eats at a speed of 11 or 12 or 100. The answer goes from no to yes, and it never ever goes back. That's exactly what we need. Now, to make our search really efficient, we need some good, tight bounds. So, what's the slowest she could possibly eat? Well, 1 banana per hour. And what's the absolute fastest she'd ever need to eat? Think about it. It's just the size of the biggest pile, right? I mean, eating any faster than that on any given hour is just wasted effort. So there we have it. Our search space is perfectly locked in. So here's how the logic plays out in each step. We pick a speed right in the middle of our current range. If she finishes on time with that speed, great. That means our answer could be this speed, or maybe, just maybe, an even slower one. So we can totally discard the entire upper half of faster speeds.
But if she's too slow and doesn't finish, well, then we know we have to go faster, so we discard the entire lower half. See how that works? We just keep narrowing it down, chopping away possibilities until we land on that one perfect minimum speed. Now, this pattern is incredibly powerful, for sure. But like any superpower, there are a few common traps that people fall into. So let's quickly talk about how to sidestep them so you don't get tripped up. Okay, the number one biggest mistake is when your yes or no question, your predicate, isn't actually monotone. If the answers can flip-flop from yes to no and back again, binary search is just going to break. Other big ones are choosing the wrong search bounds to begin with, or getting an off by one error in your code that creates an infinite loop. That's a classic. Oh, and also trying to check for direct, perfect equality when you're working with floating point numbers. That's always a recipe for disaster. You know, getting a handle on this pattern isn't just about learning one specific algorithm. It's really about adding a whole new superpower to your problem-solving toolkit, one you can use all over the place. I mean, just look at the massive difference in performance here. A simple linear scan, that's going to take time proportional to the entire range of possibilities. But binary search on the answer, it takes time proportional to the logarithm of the range. When you're dealing with really big numbers, that's not just a small improvement, it's an absolutely astronomical one. And hey, if you ever find yourself in a coding interview, here's a golden piece of advice for you. Don't just silently code up the solution. You need to explicitly state your predicate, say your yes or no question out loud, and then briefly explain to your interviewer why it's monotone. This shows a way deeper level of understanding and it'll really make you stand out. And believe me, this isn't just for tricky coding puzzles. This exact pattern is used all over the real world. We're talking about things like load balancing traffic across servers, figuring out the right resource allocation for cloud computing, setting smart rate limits on APIs, and even optimizing complex task schedules. It is a fundamental tool for building efficient systems. So if there is one thing you remember from all of this, let it be this three-step process. First, define a solid monotone predicate for your problem. Second, choose tight, logical bounds for your search space. And third, unleash binary search to find that perfect boundary between what's not feasible and what is. This really shows how one single, powerful pattern can be the key to solving so many different kinds of problems. So now that you have this new tool in your belt, here's a little challenge for you. How would you apply this exact same logic to solve a different problem, like finding the minimum capacity needed to ship a bunch of packages on a conveyor belt within a certain number of days? The pattern is identical. The only thing you have to change is the predicate. So, what would your yes or no question be for that one?